You're back. It's good to see you again. Welcome to Studio 720, high atop Chapel Hill. This is MBA 720, Technology Strategy and Business Innovation. Once again, I am your excellent host, Professor Al Seegers. Good to be with you here today. So very excited. I almost could not sleep last night for thinking about what we were going to talk about today, some of the information that I'm going to share with you today, and some of the things that you're going to see. Absolutely amazing in terms of what's going on out there in the field of technology. And today, machine learning, also known as artificial intelligence. In fact, what you're going to see today is that machine learning has a huge umbrella. Again, there are a lot of technologies under the machine learning umbrella. Some of that is artificial intelligence. Later on, you'll see where robotics starts to play into that. Very exciting field. But today what I want to do is really concentrate on, again, the greatest hits, the things that I see as being the most interesting of an incredibly innovative field. So again, impossible to cover everything, but it is possible to show you the major trends and the major technologies out there. Now, in terms of my expertise, in terms of what I have done and what I'm working on now, this is actually my sweet spot. This is my jam, as we say. That term is probably outdated already. But in any case, this is the sweet spot. This is the area where I've worked in most. Started my career in computer programming in the area of artificial intelligence, and still work quite a bit in the area of artificial intelligence. One of the companies that I'm working with now, which is really an interesting company, is called Quantify, Quantfy, leave out the I. You can check them out on the on the net. And very exciting field in terms of what we're seeing in technology. Again, I want to assure you that what you're about to see today is futuristic, even though these technologies are in operation today and are evolved. Their manifestations are pretty obvious and I think very promising out there. But also what you're seeing here in this frontier are technologies and a world of technology that will be on the front line of making the world a much better place in terms of the environment, in terms of commerce, in terms of healthcare. We're going to take a look at a couple of technologies today, particularly quantum computing, that will actually lead the way in research that will help to combat a lot of the healthcare issues that we see today, including COVID-19 and other very harmful viruses that we have out there in the world. I mean, it's not just COVID-19. There are many infectious diseases that this technology will actually be useful in combating and treating. So it is a world of extreme opportunity out there. And I just want to pause a minute to really tell you that in terms of what we're about to see in technology, it's nothing short of another revolution. There's going to be new products, new services, a whole new frontier out there that is just waiting for students like yourselves, people that are interested in business and in inventing these new models of commerce and new models of value to come out there and imagine and create. So the opportunity is huge out there. I'm so excited about where technology is going and some of the new frontiers that are being pioneered out there. So let's jump in and let's take a look at the world of machine learning. Now, a lot of what you're going to see here is going to require a little bit of explanation and a little bit of mathematics, but I know you guys can handle it. My promise to you is to make this accessible, to make it exciting, and to make it fun. And that's what I'm going to do. Most of the things that you see here actually have fairly fundamental foundations once someone is able to share it with you and to explain it to you. And that's my job here today. Um, and if I get a little giddy and a little excited about it, just excuse the enthusiasm. But this is certainly an area that I'm very fond of and have worked in for a long, long time. It's just been absolutely great. So let's jump back into our presentation format and move along the way here. And here we go. Machine learning. Now, one of the things that's really interesting about machine learning is the definition. It's sometimes poorly defined. It is not well understood. We're going to change all that with this presentation. You will be able to understand exactly what it is. And here's the good computer science definition of it: the ability to harness collective processing, storage, and connectivity of multiple devices. Now, part of that processing and part of that storage and part of that connectivity is not only to collect what's out there, but to gather inferences and to develop new structures of data. So it's not only just collecting it or moving what's out there. What machine learning does, which is different, is it creates other data, it creates other rules, it creates new knowledge or new knowledge constructs. So not only are you moving it around, but you're analyzing and creating. And that is the heart and soul of machine learning. Machine learning generally in the computer sciences is the broader umbrella for artificial intelligence. Artificial intelligence fits under that. Sometimes you'll see it in reverse, where artificial intelligence will be the bigger umbrella and machine learning may be a sub-umbrella underneath it. But staying true to the professors that I worked with and to the Google and to the IBM definitions of it, we're going to talk about machine learning with artificial intelligence being one of the umbrellas on it. Now, again, this is a huge bucket of a lot of technologies, hundreds of technologies that we could talk about individually. Just know that they are all doing the same thing. There is a common core in terms of what they're doing, and that is creating new data constructs, giving us insight into data that we may not have been able to see before, and searching for data that we may not know is out there, but that the machine recognizes might be important for that data decision. And let's just take it a step further, because we're going to see it in robotics and interacting with us. That is part of the machine learning experience out there, and it's very exciting. Now, don't start to have visions of Skynet and of Westworld and of intelligent machines that are taking away our livelihood and changing the world in very dramatically bad ways. That's not what we're talking about. It makes for great press, makes for great movies. I mean, I really enjoy Westworld. It's a fun show to watch, but it's not really what the science is all about. Basically, if you think about the world around us, you've got technology that is generating and moving a lot of data. Now, we saw that in pervasive computing. We saw some of that in the wireless mesh networking, even in 3D printing, where you've got technologies that are not only processing and storing information, but they're moving it around. And so if you've got all of this data out there and you've got all of this potential information, how do you make sense of it? How do you know what is right for a decision? How do you know what is relevant? More importantly, what data is not relevant, which is that's a filtering function. Well, that is the role of machine learning, that we as human beings cannot possibly process the amount of data, and yet we seek to solve more complex problems. Now, I want you to think about that just for a moment. It's kind of interesting. You may think that, well, computer technology's here, you know, great, it's wonderful, and it solves a lot of problems. You are correct, but there are bigger problems to solve. There are bigger mathematical equations. There is a whole world of the unsolvable equations that haven't been solved, DNA sequences that have yet to be mapped and solved that are out there. So yes, I think in society and in our technology, we have come a long way, no doubt about that. But I don't want you to ever think we have hit the finish line. We have put our toe on the starting line, and maybe we're running the first 100 yards of a potential 1-mile run. So there's a lot more out there. So the problems that can be solved, such as trying to find combinations of treatments for infectious disease, understanding how cells combine to create things that might harm us later on in life. All of these things are unsolvable by today's technology standards, even when we combine the expertise of a physician or a decision maker with the technology that's available. Machine learning is that step to help us better understand the amount of data that's out there, to harness additional computer processing power. We're going to see that in quantum computing in just a moment. And to be able to embark upon a discovery of problems that have been unsolvable up until now. Now that's such great news for you and me, because it's going to open up new industries. It's going to open up new businesses, new ways of making decisions. It's going to change management. You know, how you and I interact with technology, how we use technology is going to change. And that technology is not going to be totally reactive to us. Now what we're talking about is the technology being proactive and being interactive. And so if you think about sort of how it's evolved, you know, you think of technology in its basic state as being reactive. I go in and I do a sort on an Excel spreadsheet and it gives me information. That's technology reacting to the to us, to our commands. Nothing wrong with that. That's sort of stage one. Stage two, the technology might proactively sort the data, knowing that I'm trying to understand something about that data in terms of its order, something different from its raw appearance. And so the technology proactively goes in and does that. The third stage is interactivity. Think about that, interactivity. That is where you are interacting with the technology to try to solve some particular issue. That's the frontier that we're going into. It's very exciting. It shouldn't scare you. It shouldn't concern you. This is going to open up an incredible amount of possibility, an incredible amount of educational possibility, an incredible amount of healthcare options that just weren't available to us until now. So let's jump in. Let's learn a little bit about it. As we usually do, we're going to go in and give you a definition. Now look at that definition from 1959. I chose that on purpose to tell you that this is not something new. Scientists, research labs, students have been at this for quite a long time. Again, when I entered my undergraduate study, this was sort of a field that was pretty well established. It's been around since 1959, which is before my time, but it's been there for a long time. And so I think what's really changing about it and why it's become so more obvious and upfront, again, is just the evolution of a lot of different technologies that support it. Computational power, programming languages, robotics, a lot of things sort of come together to put this right at the forefront again, and the collection of data. I think that's what's really driven it, is that you've got devices everywhere that are collecting data from social networks. I'm going to show you some work that's been doing, it's actually a project that I'm working on with MIT Media Lab that looks at social media data and tries to draw from it different inferences, different constructs. It's very, very interesting. So I'll show you some of that work later on. But the explosion of data and our ability to organize it, process it, make sense of it, that's kind of the difference now. So things that could not talk suddenly have a voice. And so when objects and when sensors can pick up that voice, suddenly we have new forms of data, which gives us a whole lot more input into computer algorithms, into programming language that can give us a whole different perspective on what's going on around us. So here's the machine learning definition: field of study that gives computers the ability to learn without being explicitly programmed. That is the definition. That is the definition. Where a machine, and now think about this carefully. This is kind of a cool thought. If you have a machine, a computer, just your desktop or whatever device you have, your mobile device, if it has the ability to learn without being explicitly programmed, it is inferring different things based on the way you use it. It is proactively going out there and finding stores that you may be interested in. Now, again, this goes on all the time. If you hit your Facebook page or your Instagram account, you might be hit with that technology suggesting to you things that you may be interested in. And it might be scary sometimes as to how correct it can be. When that technology starts to infer and starts to learn, then it's crossed the definition of machine learning. What's really good about it is if that device can teach other devices. That's where you're really starting to see a network effect of artificial intelligence or machine learning, when the machines start to coordinate each other. Now think about that. One machine learns, one machine starts to draw inferences, and then it moves that programmed knowledge, or that artificial intelligence, if you want to call that, to other machines. The other machines learn that, and they are also informing the first machine of things that they have learned, or things that they have created because of what's been given to them. Now you may think, oh my God, what could possibly do that? Blockchain. That's what blockchain is all about. And that's why in a few minutes we're going to study it and why it appears under this umbrella of artificial intelligence. It is part of that idea, part of that field of study and that technology, where machines are teaching each other or informing each other about a transaction. So if I go to the bank and borrow money to buy a house, then that machine is communicating with other machines that might have an interest in that transaction. My bank, my brokerage firm, real estate databases that capture that information, as well as city and county government that register me as the owner of that particular piece of property. Blockchain is that technology that would share that transaction across multiple machines that would have a vested interest in that transaction. All of those machines can also communicate back to the primary machine other objects or other things they've learned about that transaction that are relevant. And so that is the ability of machines to teach each other and to learn from each other. Fascinating, right? It's amazing. Now, here again, I don't want you to get too caught up in this. It's easy to do because I'm obviously excited about it. I love this stuff. It's a tremendous field. But one of the things you have to do is start to think about what new business models. What does this mean? What does it mean for financial services? I mean, financial services is going to be turned on its head with machine learning and with artificial intelligence. What does it mean for real estate? If you're someone that's going into that field, what does it mean for contracting? What does it mean for new products, new services? What does it mean for healthcare if we can suddenly coordinate a lot of patient records using artificial intelligence and machine learning. It's going to change a lot of stuff. That's very exciting. It's not going to take away business opportunity at all. It's going to expand it. It's going to explode. There's going to be a whole lot of new businesses out there and a whole lot of new opportunity. So let's go into the basic building blocks of machine learning, go into the code, sort of into how it works. There are basically four components to it. There are algorithms, conditional probability, Bayesian inference, and data. None of these things are hard. In fact, they each have sort of an interesting background. So let's jump in first of all to algorithms. There you see it. This is actually computing code. This looks like C, C++. And what you're seeing here, let's kind of go into just a little bit of the code. If you go to the top left-hand side there, you can see unsigned integer, constant size. What's going on here is it's defining a size for a data structure in there, a vector of columns. And you go into the middle part there, line 24, and you see 4 for the unsigned integer, I equals 0. Then you get conditional probabilities, or conditional computing code. That's an algorithm. Basically what's going on here, this is computer code that is telling the machine what to do for a particular instance when it encounters a certain data object in there that registers a certain value. So the basic building block is what we call if then else type of program. If A occurs, then B, else C. And that's the building block of algorithms. And that simple little phrase, if then else, really underlies a lot of artificial intelligence, or certainly a lot of those programming languages. There are specialized programming languages that can be used for artificial intelligence that are a little bit more intuitive. You've seen structured query languages, SQL, which is more of a human interface into the code of gathering data using machine learning. And that's readily available out there. It's highly likely that if you haven't already used some structured query language, you will at some point to pull from data things that have conditions. Your structured query language converts into code like this that goes into a database, and the algorithms pull from it the things that you want. It's really not that hard. It can be tedious. There's certainly a lot of exceptions that happen in machine learning, or if you're programming robotics, and that was an area that I was in during my undergraduate and graduate school PhD program. We used relay language to program robots, and you would think that you would have every condition covered, you know, that the robot would be able to handle every exception. The robot would be able to anticipate almost any need. And then something would happen. You go, oh no, I never thought of that happening. And then you have to go back in and put in more relay language to actually have the robot do what you want it to do. So it is very iterative. It is very trial and error, but it is becoming something that is certainly these days much easier to do because of the programming languages that are really dedicated to that type of application. It's actually, some of those languages are actually quite good compared to the languages that we used way back, you know, in the, I'd say late 80s or early 90s. You're really seeing a big improvement. The language that we used back then, certainly in undergraduate around 1987, 88, was called Intellect by IBM, which was a programming language specifically for artificial intelligence, and that's now been replaced by Lisp processing and others that are quite good. So just know there's a whole collection of programming languages out there that really get into this idea of basic algorithms, telling the computer, if this occurs, then do this. If not, then you do something else. It's kind of like when you go to a red light. If the light is red, then stop. If else speed up, you can make it, if it's yellow or green, depending. Your algorithm may be if it's yellow, if it's red, then stop. That's my wife's algorithm. Yellow to her means stop. Yellow to me means speed up, you can make it. All right, that's individual coding. So here we go. The second piece of it is conditional probability. Don't be freaked out by what you see. It's the probability of A given that B has occurred. There are mathematical equations that can calculate the probability of A given that B has occurred. So you see this all the time, I think, in sports and other games of chance, I would suppose. I mean, let me just kind of give it to you in the event of playing cards. If you're playing cards, the probability, the most likely probability on drawing a card, if you're playing 21 blackjack, is to get a 10. You got jacks, kings, queens, and of course tens that are the value of 10. So you know going into the game that the likelihood of a draw is probably highest on a 10. Very helpful when you're at a blackjack table. However, if a 10 has been drawn, what is the probability of drawing another 10 after that? Well, that is conditional, based really on the cards you see on the table. So if you're a card counter, you can actually develop some conditional probabilities by what you see on the table. And if you play the game, if you play the table long enough, you can start to understand what the probability of a 10 is given that a jack has been drawn or that a 2 has been drawn. You can also use this if the dealer has drawn a low card. So the probability of the dealer busting, given that he or she drew a 2, that probability is higher. I can tell you that. Low cards on dealer side in a blackjack game are the advantage of the player. They're likely to bust if they do. It doesn't mean they're going to bust all the time, but there's a conditional probability that they will bust drawing the low card. Well, this is the mathematical representation of that. Long story short, I've been banned from playing cards in a couple of casinos in Las Vegas. So this technique does have its drawbacks, but it does kind of get behind games of chance. What is the probability of something happening given that something else has occurred? That's conditional probability. Well, if we combine that with Bayesian's law, and this is an interesting one, Bayesian statistics really gets into posterior distribution, Bayes' theorem itself. It gets you into this idea of what has happened, again, conditional probability, given that something else has happened. So Bayes' law takes this just a little bit further. Now, here's the interesting piece of it. So your factoid for today that you might not have learned had you not taken this class. Bayesian inference was actually developed by a priest. And what his goal was to prove the existence of God. And so in his efforts to do that, he developed an incredible statistical theory and theorem that is very, very useful in trying to understand probabilities of something happening given that something else has happened. Well, these are mathematical formulas, conditional probability, Bayesian statistics, that go into artificial intelligence and machine learning. So it's built on a lot of statistics. Now, the reason I'm taking a little bit of time here and kind of moving you this way is to let you know that this is inference. It's probability. As I told you before, if we go back to conditional probability, dealers can draw low cards. So let's say the dealer is showing a 2 or a 3. Well, at that point, I'm willing to sit on a 14 in the game of 21 because my belief is, given that the dealer, he or she has drawn a 2 or a 3 or even a 4, that they're going to bust, and so my 14 is going to win the hand. That won't happen all the time. Now, the probabilities are greatly in your favor. This is a good play if you're playing blackjack, but it doesn't mean that it happens all the time. So one of the things that's interesting about the world of artificial intelligence, it does kind of mirror human reasoning, and it mirrors the real world. It can give you the probability of something happening, but that doesn't mean that will actually happen every time. It just means on average, that dealer will bust on a low draw in a game of 21. So what goes into this as well is data and the interconnections between data. So that's the final piece of it. And as I told you, what's really driving this revolution, what's really making artificial intelligence incredibly interesting is data that didn't have a voice now has a voice. Things that were undiscoverable in the past are now discoverable. I'll give you an interesting example of that. When Ancestry.com started its DNA testing, they thought that there might be some interest in it. They didn't realize the explosion of people that would want to know more about their background. So suddenly, Ancestry was overwhelmed by people trying to discover who they really are. Well, 23andMe, another service, another digital service that can sort of categorize your DNA and tell you where you're from. It can give you, again, now, I don't want to shatter any impressions out there, but what it's doing is using Bayesian inference to tell you the probability that you might be from some country. So if you've always thought you were Irish and you send in a DNA test and it says that you might be 33 or 45% Irish, it's telling you based on conditional probability, based on your DNA strand, that that's where you might be. That's where your ethnicity lies. It's not perfect. It's not going to show you exactly that you are 100% this, 80% that, whatnot. It doesn't mean that it's not useful. There's just going to be some statistical probability in there. What is useful about that is that DNA that you provide gives a perfect sequence of who you are that can go into computational data to compare other genetic types to start to understand how disease might spread, your probability of getting that disease, and why you should be worried or why you might not be worried. So, for example, in COVID-19, one of the possibilities there is if we had DNA sequence on everybody along with data on who is catching this and who is not catching it, who might have the virus but it never manifests. There are genetic sequences that would be able to tell us the likelihood of you not getting the disease, perhaps you're just completely immune to it, of you getting positive but you never develop it, or the worst case scenario, you test positive, you get it, and it turns into something not good. That would be what we could use this type of data for. That's where we're going in the future. So if you had a pandemic like we have now, certainly artificial intelligence, machine learning would be a very quick way to really understand what it is, what that disease structure looks like. We could understand DNA structure that has different reactions to that particular virus. We could do this instantly. I mean, this could be done very, very quickly. And again, to kind of continue the example, we could also know what treatments might be most effective on that. So there is good news. So I don't want you to think for a minute that, what you're experiencing, certainly during our time together, is something that is bigger than the technology and the know-how that we have. Believe me, I think that we're embarked on this frontier. If we were further into this frontier, then you wouldn't see some of the conditions that we're now experiencing. So the future is very bright when it comes to looking at infectious disease, because now this DNA data is coming in. We get that married to data on different reactions to a particular infectious disease. It certainly gives scientists a lot more insight into how such a thing can be treated and how such a thing can be avoided, and predict different reactions to it. And you don't have to rely on mainstream media. And I will have to say, I'm just going to take a moment to step on the the stool here and preach. So much of what you see in mainstream media about technology is it's just so wrong. It's just not. I mean, it makes for a good story, but it's just so wrong. So stay true. We're going to talk about that in just a minute, but always think about things from a calm, logical standpoint, and I think you're going to get a better insight into anything that's going on out there. So that is machine learning defined, and it's 4 basic building blocks. So let's now take a look at some of its applications. So again, very excited about what you're going to see here. These are some of the best technologies. The first one that I think is incredible, and this is a project that I'm doing with MIT Media Lab. So this is University of North Carolina, MIT Media Lab, and the Defense Advanced Research Projects Agency, also known as DARPA. And so what they do, DARPA bestows grants upon people like me or university professors to do research into different types of things that are of interest to national security, to the betterment of the country, all sorts of things that are done here. So they're a major funder of university research. And what was really interesting in this project was to try to understand the data structures and visualize those data structures in social media. Now, social media, I'll have to say, it's something that I'm a little bit enamored with. I wouldn't say that I'm a huge participator in it. I've got the usual Facebook account and the Instagram and certainly a Twitter account and all that. But when you start to dive into these different accounts and dive into the way data manifests itself in terms of visualization, you really get some deep insights. So let's take a quick look, just to give you some context here, of the art of data visualization.
In the arrangement of a visualization, every single pixel should testify directly to content. As Johnny Ive, the great Apple designer, said, we spend most of our time getting design out of the way. It's got to get out of the way because it's about the relationship of the viewer and how they reason about the content. Style, the aesthetics, cannot rescue failed content. If the words aren't truthful, the finest optically letter-spaced typography won't turn lies into truths. There are enormously beautiful visualizations, but it's as a byproduct of the truth and the goodness of the information. The big steps in showing information began all with cartography about 6,000 years ago when the first map was scratched into a piece of stone. And that has wound up now with the most widely seen visualization in the world, which is Google Maps, where people are using a visualization to actually do something. The next big step was the development of real science. Galileo got his telescope going. He saw things that had never been seen before. He made beautiful drawings of sunspots, and he watched the sun for about 40 days, and he did engravings of the sunspots, so he visualized what he saw. And so the history of visualizing data is very substantially a history of science.
Data visualization is not just some airy-fairy creative process, but it's actually a very linear process of decision-making that you can do based on some few basic principles. 3 things should inform your design always. One is you as the designer, what you have to say and what you want to communicate. 2 is the reader. That reader is not you, and they're going to come with their own context and their own biases and their own assumptions, and you need to account for that. And 3rd is the data itself and what that has to say and how that informs the truth. There's a lot of subconscious brain activity happening. We evolved for it to happen that way. We evolved to see things and make snap decisions. Are all those lines in the graph just dried grass, or is that a tiger that's coming to eat me? We have to be able to recognize those patterns right away and make snap decisions on them in order to survive. And that can be an advantage as a designer. You can communicate a lot of information very quickly because we all have brains that are designed to recognize patterns this way. But also, there's the emotional impact. We react to design and to art and to the aesthetics of a piece just as much as we react to the information contained in it. And so if you want to change someone's mind, if you want to change someone's behavior, sometimes presenting the information in a visual format is the fastest way to get them to engage with that information.
Truth is one of those ambiguous things that you can't really define and probably changes and evolves the more understanding you have. Data itself is a result of research, so I would say that data is just a clue to the end truth. I think a successful infographic tells a story. It communicates hopefully accurate and sometimes complicated data in a way that many people can understand. I think the first step usually is always dig really deeply into the data ourselves and find each key point and create a hierarchy and a narrative out of that story. When you start to merge different pieces of information and when you start to learn really what it's all saying, the narrative is clear. The one key fact that everything can revolve around is the hero of the piece. There's one single piece of data or insight that people respond to and kind of encapsulate the whole vision, and then invite people in to see the nuances and all the rest of the story around it. When you look at a piece, it's successful when it translates data from something that's complicated to something simple, when it communicates a message that otherwise would have taken somebody hours to digest and find in an instant.
My deepest interest lies at the boundary between data and culture. Data are measurements of something. In very many cases, those some things that we're talking about are human systems. We're dealing with data systems that are larger than anything that humans have ever built or experienced before. And these really large systems, things happen within them that are emergent. For example, A-Change combines shot footage from airports for pretty much every airport in the world, and then air travel data as well. So the central idea was to show people that every time that you're in an airport, you are standing on the surface of a system that is almost too complex to comprehend. At any given time, there are more than 1 million people in the air. And so there's another purpose of data visualization. There's revelation, which is show us something that we've never seen before. This is, for me, much more exciting. Anybody can visualize data in Excel and see some bar charts. For me, it's about showing them something in this kind of loose narrative frame that they can interpret. So we show them some pieces of the picture, and the idea is that they can sort of stand back from that and watch it pass for a little bit and come out of it with some deeper understanding. Part of it is leaving it open to interpretation, but part of it is also not really knowing. I don't have some masterful understanding of this system that you don't. I have some ideas about how these systems might be changing and how they might be growing and how they might be important to our culture and society. And I want to share some of those ideas with you, and maybe you can put together something that I wouldn't have been able to put together.
I think in general, audiences are a lot smarter than a lot of people think. So it's not know your audience, it's respect your audience and really know your content. That's what you should be knowing and reasoning about. Look after truth and goodness, and beauty will look after herself. You want to see to learn something, not to confirm something. We usually see to confirm things. It's very economizing for the brain. How can we see not to confirm, but to see to learn?
Wow, isn't that great? A couple of things that I want to talk about there in what you just saw. Number one, data visualization in and of itself is an amazing field. There is a lot of interest in it. There is a whole lot of companies that are looking for specialists that can take data and create visual forms of it. Now, that's not just a computer science issue at all. That is something that business people, certainly those that study social sciences, should be able to do very well. The second point I want to make is a discussion in there about data for revelation. That is what's so exciting to me about data visualization, is that it's not just to organize it in pretty charts. It is to reveal, that the data reveals to us its story. The data has a chance to tell its story. So when I'm thinking about this as a researcher and in working with companies, what we really try to do is get data to tell its story, to put it together in a way that it visually can tell us what is happening. And I think revelation is one of the key pieces. I think in MBA programs, bless our hearts, we're very good at teaching how to present data, but we're not really great at teaching you guys how to get into the revelation of data. Well, this is the science of that, and this is, and I'm going to show you some examples in just a moment here, that is really sought after by businesses and by science institutes, is how to reveal it. The final point, third point I want to make, is the final one mentioned there. We look at data and we want it to tell us something. We don't look at it to learn. And I think that is so key. It's a subtle thing. Not looking at data to confirm, but looking at data to learn. We are born, we are programmed to look at data and have it confirm things that make us feel comfortable. So in the tiger in the grass example, your initial reaction would be, it's not a tiger in the grass, it's just stripes in the grass, because that makes you feel safer. It makes your world in balance. You have to look at data to learn. If those stripes are moving in the grass, it's a tiger, run, you're not safe. So we have a high confirmation bias, amongst us, and we have to teach ourselves to look at data to learn. So I think that's just a powerful video on the art of data visualization. If that's interesting to you, if that's something that, say, hey, I think I might have some talent for that or interest in it, I mean, I highly encourage you to pursue that. That would be a great way to approach project number 2, give a discussion about data visualization, learn a lot about it, and who knows, maybe you can find a career path that will put you into that spot. It's, to me, very, very fascinating. So let's go to some practical application. This is a project from MIT Media Lab, UNC, and department, the Defense Research Department, DARPA, the Advanced Research Projects Agency. And what we're trying to do here is take a look at social media. So what you see here is called a bubble account. Each circle is a Twitter account. The size of the circle represents the number of followers. This is pretty easy to find. Now, artificial intelligence is what we're using to go in and comb those accounts. So we've got algorithms that are going out and, for lack of a better word, trolling Twitter accounts. And all we're looking at here is the number of followers. Color reflects the content. Now, the content is actually done, or the determination of content is done through artificial intelligence. It's way too difficult to have a PhD student or someone go in and read the content of the Twitter account and determine what that content is. However, we can send algorithms, we can send artificial intelligence or machine learning algorithms in to determine the content of that based on the words that are used, the phrases that are used, and the content that is in there. And that can be done very accurately, very accurately. There's not a lot of in between there. And then what we can do is we can map those into this spatial diagram, which you see here before you. Blue is anti-Trump, red is pro-Trump, and you could also just say for any president, so it doesn't have to be just Trump, so any president, if you're going in at any point in time to take a look at these. Pink is progressive. Notice how the progressive pink diagrams kind of interweave in there. They're not too far left, not too, more left than right, but not too far left on the diagram. Orange is mainstream left. You can see that mainstream left, I think sort of in the middle there. The yellow Democrat, purple Republican, and green conservative. So you can see here sort of the idea of media mixed with Twitter accounts. So the Twitter accounts of media outlets with individual accounts. One of the things that you can see here certainly is the idea that there is a little bifurcation, particularly of individuals. Take a look at the blue and the red on the left and the right there. You've got the purple and yellow that are actually more centered in this diagram. A lot of the green on the outside, the conservative media, and the orange mainstream left media. So it kind of, to me, it's got sort of a kidney shape here, is not that surprising. But what it does reveal, if you're looking at the revelation here, is in fact and in science a digital divide, or not a digital divide, but certainly a political divide in terms of Twitter accounts. It's not surprising, but that dispersion and the middle piece there is interesting. It is interesting. And what we would do here, what we are doing, is you take different snapshots in time to see. So we've got this algorithm working right now. Maybe, I hope, maybe I can get that data back in before the end of the class and show you how this is changing during the pandemic, changing during election season. There were some interesting changes in election season, particularly before the primaries, the Democratic primaries, in terms of how some of the progressive bubbles shifted in content and extremity. So you watch this over time just to see how opinion is changing in content, but it's a nice marriage of data visualization and artificial intelligence. You couldn't have done this even 10 years ago. You couldn't do this. It would be impossible to do this. Now it's possible to see data in a visual form because of artificial intelligence. It just gives you the possibility to do that. So what was once voiceless is now voiced, and we can actually see it in data visualization. Here's another one that's kind of interesting. This is Twitter accounts plotted by political homogeneity. Now, what political homogeneity means is it's the Twitter account is followed only by progressive accounts, and one followed by only conservative accounts. So you see to the left there, again, you're seeing that, I think, a fairly obvious inclination, but now it's showing up in data that if there is a progressive account, it will most likely be only followed by other progressive Twitter users. But notice on the left there, you see there is a good intermingling of red in some of those blue accounts, which means that there are some Republican, I don't know if you could call it less progressive followers on the left-hand side, but there is very few blues on the right-hand side. So what that might reveal is that there is a stronger tendency, or more likely tendency, that someone with conservative views would also follow someone with less conservative views than the reverse. Someone that has progressive views is not likely to follow the Twitter accounts of, or Twitter account of someone they perceive as too far right. I'm not sure that that's incredibly strong, but you can see some of it there. So if you look to the left, you see the intermingling of the red accounts with the blue, but you don't see a whole lot of intermingling of blue with the red. The green, they're there. That's the missing middle right there. So again, you're seeing polarization of Twitter accounts based on content, and not to make any other comment on it than say it exists. And we're following that over time. Again, it'd be interesting to see how that changes, or how it's changing right now as we speak, because we've got those algorithms running right now across Twitter accounts. Here we go. So what we did here, we just looked at media accounts. So this is media. What's really interesting is who follows whom. So look there in the middle, you see the CNN bubble to the lower, a little bit left. There you see the CNN bubble, and you can see who follows CNN accounts. And what would happen, what you see here, is that left-leaning type of accounts are followed by other left-leaning accounts. And so what you're seeing is a real polarization of media, meaning that there's very few in the middle. In the middle would be where your account is followed by both left and right-leaning media outlets. And you can see it's true for the right-hand side too. If you're a right-leaning media outlet, then you are followed or you're co-citated by other accounts. So what you're seeing, if you just look to the right there, what it means is that all those Twitter accounts on the right-hand side are co-citationing or co-citing other right-leaning accounts. They don't cross the line over there to the left. So you're not going to see CNN citing anything on the right. They're only going to cite information they get on the left. This is interesting. I don't think it's surprising, but it's also dangerous. So what it means is there's very few green. The green in the middle would be a neutral site, if you will, that is citing both the left, the blue, and the right, the red. That would be more of what I'm going to go ahead and say it, but I'm not sure I can prove it completely right now. But that would probably be the most balanced media. How about that? The most balanced of all media outlets is the Wall Street Journal. You will see them citing stories from the left and the right. They are the middle, and we've done some research on the accuracy of their stories vis-a-vis other outlets, and it's the great balance. Wall Street Journal tends to come out very, very good, certainly better than Washington Post sometimes on the left. Not to down them. If you read Washington Post, that's fine. What you just need to know is that the Washington Post is going to tend to look in its blue world there for backing data. They're not going to look to the right. And for those that read information on the right, the Examiner, Fox News is down below Breitbart there. Fox is not going to look to the left over there for co-citation. Typically, they're not going to do that. So that's just the way it is. I mean, I'm not going to make any political statement. I'm not really a political person myself. I'm too busy worried about technology or loving technology, but that's it. But I would stand right behind that and say that is the way it is. We've presented this out to some congressional subcommittees, and I think they like it this way, to be honest with you. I think that this actually serves their view of politics very well. Kind of sad in a way, but what we were hoping for is more in that middle. But you can see it's very bifurcated, left and right. So just to tell you, that's just the way it is. So again, this is data revealing to us things that I would say, again, 10 years ago, 5 years ago, we wouldn't have been able to run that. We wouldn't have been able to run that study and get that kind of data out of it. So good. That's data visualization. Very excited about that technique. So much more to come when you add VR, when you add other technologies to data visualization, then you can really see that that's going to be an exploding area. What I want to talk about next is one of my favorite applications of artificial intelligence. Again, something that would not have been possible years ago. I would say probably even 2 years ago, is the Event Horizon Telescope. Now you can read all about this project in a great book. It's called Einstein's Shadow. I highly recommend it. Absolutely great. There is another book that chronicles this project and talks about it. It's called Ideas in Innovative Organizations. It's my book, and I talk about the Event Horizon Telescope, the Human Genome Project, and a lot of the other what I call super super projects in the book, things that are really outside the ordinary, and chronicle them in the book. So let me talk just a little bit about what Event Horizon Telescope does, and you're going to see some great video from Katie Bauman, who's one of the artificial intelligence programmers on the project. This is a project that I got to study in depth. It was fascinating to be there and to be embedded in the project and to see how it works. Basically, this gets back to what we talked about earlier in mesh computing, radio waves. Do you remember that? Do you remember when we talked about hertz, megahertz, kilohertz, thousands of cycles per second, megahertz, millions of cycles per second, gigahertz, billions of cycles per second. Do you remember that in the frequency spectrum? Well, now it's back. If you take a look at any astrological phenomena, a black hole, a planet, or a star, anything in our galaxy, they emit radio waves. And so if we're going to explore deep space, the way to do that is to capture those radio waves and turn those radio waves into charts, into images, into useful information that helps us map the galaxy. And that's what the Event Horizon Telescope, it's what it does. Now, if you take a look at what they're after, what they want to do is photograph the black hole that is at the center of the Milky Way galaxy. Now, if we're able to photograph a black hole, now again, the black hole that sits at the center of our galaxy is emitting radio waves. We can read those radio waves with a radio telescope. That's how they do it. But to reach into deep space and to accurately read those radio waves, you need a telescope about the size of the planet Earth. And that's not possible. So what the Event Horizon Telescope project did is it unified telescopes across the globe to create digitally a radio telescope the size of the Earth. And the goal was to photograph the black hole at the center of the universe. Now, why would we do this? Why would we care? Well, we're trying to understand the origin of the universe. We're trying to understand how the universe is created and what the role Earth plays in the universe. It's deep space exploration. It is incredible. And so the goal of the project is to take a picture of this. Now, why it's called an event horizon, just to give you a little background, a black hole is so dense, it is so heavy in theory, and this is Einstein's theory. So we go into Albert Einstein and his theory, and that's why the book is called Einstein's Shadow, is that even light cannot escape from it. And there, ergo, is why it's called a black hole. However, light would circle around it. And that spinning of the light would become what's called an event horizon, the event horizon of a black hole. And here you can see it illustrated in this diagram. So there are phenomena that can be measured in a radio microscope that would then be able to be assembled into a photograph or a picture or an image of this particular object. Now, the way that's done, the way that this is created to render the image, and this is the actual image. So you can see here, this is the image that Dr. Katie Bauman, who you see right there in the photograph, this was the moment that the image became visible on her computer, and she took a photograph of this. You could see the relief in the room and the joy, I think, and the exhaustion in the room to render, this image. Now, the way this is done is you would take regular photographs of almost anything. So just imagine your iPhone full of photographs right now. What we would do, we have to have some raw material to create that physical image. So what you have from the black hole is radio waves that are hitting the telescope. The telescope would read those radio waves, and then it would take those radio waves and assemble a photograph. Now, the way that photograph is assembled, so again, imagine all of your photographs on your iPhone. If we chopped them all up into small little chunks, small little squares. So any photograph you might have taken of yourself, of your pet, or if you're like my wife, she loves to take pictures of food that she's sees at a restaurant and send it to my son and say, "Ha, here's what we're eating tonight." Why, I don't know, but in any case, whatever photograph you might have on your phone, chopped up into small squares, and then take all of those squares of your photographs. So let's say you had 200 photographs on your iPhone. We chop them up into little squares, and we put those in a basket. Okay, put them in a basket. The radio waves come into the radio telescope. Those radio waves then hit computer algorithms that draw into the basket those photographs chopped into small little squares, and then it will assemble those squares to produce what it is seeing in deep space. That's how the Event Horizon Telescope works. Well, artificial intelligence makes that possible. It would be impossible for a human being to take those radio images and create the image that Katie is seeing on her computer. In fact, if you take a look at her laptop there to the right, those are all artificial intelligence or computer algorithms that her and her team, it's very much a team-oriented project, have written to translate those radio waves into that photograph. That photograph is made up, the raw material to make up that photograph are just pictures of everything. Just imagine this huge database of tiny little squares, pictures that have been chopped up into little squares, and it produces that image. The way that you test the validity of the algorithms is you feed it different radio wave signals to see if it keeps reproducing the same image. And in this case, it did. It was very much a feat of artificial intelligence, of tenacity, and as we're going to talk about later on in the course, sheer innovation. I mean, this is one where just some creative people get together and are just tenacious in photographing this image. This image was produced in April of 2019. What we're going to see now is a video of Katie describing that process, describing how artificial intelligence was used. And this was filmed in the form of a TED Talk about a year before the photograph was rendered by the Event Horizon Telescope team. So take a look at this and you can see the application of artificial intelligence to discover something that was undiscoverable and to have data, radio waves, reveal to us in visual form what it could not reveal to us only 2 years ago.
So in the movie Interstellar, we get an up-close look at a supermassive black hole. Set against a backdrop of bright gas, the black hole's massive gravitational pull bends light into a ring. However, this isn't a real photograph, but a computer graphic rendering, an artistic interpretation of what a black hole might look like. 100 years ago, Albert Einstein first published his theory of general relativity. In the years since then, scientists have provided a lot of evidence in support of it. But one thing predicted from this theory, black holes, still have not been directly observed. Although we have some idea as to what a black hole might look like, we've never actually taken a picture of one before. However, you might be surprised to know that it may soon change. We may be seeing our first picture of a black hole in the next couple years. Getting this first picture will come down to an international team of scientists, an Earth-sized telescope, and an algorithm that puts together the final picture. Although I won't be able to show you a real picture of a black hole today, I'd like to give you a brief glimpse into the effort involved in getting that first picture. So my name is Katie Bauman, and I'm a PhD student at MIT. I do research in a computer science lab that works on making computers see through images and video. But although I'm not an astronomer, today I'd like to show you how I've been able to contribute to this exciting project. So if you go out past the bright city lights tonight, you may just be lucky enough to see a stunning view of the Milky Way galaxy. And if we could zoom past millions of stars, 26,000 light years towards the heart of the spiraling Milky Way, we'd eventually reach a cluster of stars right at the center. Peering past all the galactic dust with infrared telescopes, astronomers have watched these stars for over 16 years. But it is what they don't see that is the most spectacular. These stars seem to orbit an invisible object. By tracking the paths of these stars, astronomers have concluded that the only thing small and heavy enough to cause this motion is a supermassive black hole, an object so dense that it sucks up anything that ventures too close, even light. But what happens if we were to zoom in even further? Is it possible to see something that, by definition, is impossible to see? Well, it turns out that if we were to zoom in at radio wavelengths, we expect to see a ring of light caused by the gravitational lensing of hot plasma zipping around the black hole. In other words, the black hole casts a shadow on this backdrop of bright material, carving out a sphere of darkness. This bright ring reveals the black hole's event horizon, where the gravitational pull becomes so great that not even light can escape. Einstein's equations predict the size and shape of this ring, so taking a picture of it wouldn't only be really cool, it also helped to verify that these equations hold in the extreme conditions around the black hole. However, this black hole is so far away from us, so from Earth, this ring appears incredibly small, the same size to us as an orange on the surface of the moon. That makes taking a picture of it extremely difficult. Why is that? Well, it all comes down to a simple equation. Due to a phenomenon called diffraction, there are fundamental limits to the smallest objects that we can possibly see. This governing equation says that in order to see smaller and smaller, we need to make our telescope bigger and bigger. But even with the most powerful optical telescopes here on Earth, we can't even get close to the resolution necessary to image on the surface of the moon. In fact, here I show one of the highest resolution images ever taken of the moon from Earth. It contains roughly 13,000 pixels, and yet each pixel will contain over 1.5 million oranges. So how big of a telescope do we need in order to see an orange on the surface of the moon, and by extension, our black hole? Well, it turns out that by crunching the numbers, you can easily calculate that we would need a telescope the size of the entire Earth. And if we could build this Earth-sized telescope, we could just start to make out that distinctive ring of light indicative of the black hole's event horizon. Although this picture wouldn't contain all the detail that we get to see in computer graphic renderings, it would allow us to safely get our first glimpse of the immediate environment around a black hole. However, as you can imagine, building a single dish telescope the size of the Earth isn't possible. But in the famous words of Mick Jagger, you can't always get what you want, but if you try sometimes, you might just find that you get what you need. And by connecting telescopes from around the world, an international collaboration called the Event Horizon Telescope is creating a computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon. This network of telescopes is scheduled to take its very first picture of a black hole just next year. Each telescope in the worldwide network works together. Linked through the precise timing of atomic clocks, teams of researchers at each of the sites freeze light by collecting thousands of terabytes of data. This data is then processed in a lab right here in Massachusetts. So how does this even work? Well, remember, if we want to see the black hole in the center of our galaxy, we need to build this impossibly large Earth-sized telescope. So for just a second, let's pretend we could build a telescope the size of the Earth. This would be a little bit like turning the Earth into a giant spinning disco ball. Each individual mirror would collect light that we could then combine together to make a picture. However, now let's say we removed most of those mirrors, so only a few remained. We could still try to combine this information together, but now there are a lot of holes. These remaining mirrors represent the locations where we have telescopes. This is an incredibly small number of measurements to make a picture from. But although we only collect light at a few telescope locations, as the Earth rotates, we get to see other new measurements. In other words, as the disco ball spins, those mirrors change locations and we get to observe different parts of the image. The imaging algorithms we develop fill in the missing gaps of the disco ball in order to reconstruct the underlying black hole image. If we had telescopes located everywhere on the globe, in other words, the entire disco ball, this would be trivial. However, we only see a few samples, and for that reason, there are an infinite number of possible images that are perfectly consistent with our telescope measurements. However, not all images are created equal. Some of those images look more like what we think of as images than others. And so my role in helping to take the first image of a black hole is to design algorithms that find the most reasonable image that also fits the telescope measurements. Just as a forensic sketch artist uses limited descriptions to piece together a picture using his knowledge of face structure, the imaging algorithms I developed use our limited telescope data to guide us to a picture that also looks like stuff in our universe. Using these algorithms, we're able to piece together pictures from this sparse, noisy data. So here I show a sample reconstruction done using simulated data where we pretend to point our telescopes to the black hole in the center of our galaxy. Although this is just a simulation, reconstructions such as this give us hope that we'll soon be able to reliably take the first image of a black hole and from it determine the size of its ring. Although I'd love to go on about all the details of this algorithm, luckily for you, I don't have the time. But I'd still like to give you a brief idea of how we define what our universe looks like and how we use this to reconstruct and verify our results. Since there are an infinite number of possible images that perfectly explain our telescope measurements, we have to choose between them in some way. We do this by ranking the images based upon how likely they are to be the black hole image, and then choosing the one that's most likely. So what do I mean by this exactly? Let's say we were trying to make a model that told us how likely an image were to appear on Facebook. We'd probably want the model to say that it's pretty unlikely someone would post this noise image on the left, and it's pretty likely that someone would post a selfie like this one on the right. The image in the middle is blurry, so even though it's more likely that we'd see it on Facebook compared to the noise image, it's probably less likely we'd see it compared to the selfie. But when it comes to images from the black hole, we're posed with a real conundrum. We've never seen a black hole before. In that case, what is a likely black hole image, and what should we assume about the structure of black holes? We could try to use images from simulations we've done, like the image of the black hole from Interstellar, but if we did this, it could cause some serious problems. What would happen if Einstein's theories didn't hold? We'd still want to reconstruct an accurate picture of what was going on. If we bake Einstein's equations too much into our algorithms, we'll just end up seeing what we expect to see. In other words, we want to leave the option open for there being a giant elephant at the center of our galaxy. Different types of images have very distinct features. We can easily tell the difference between black hole simulation images and images we take every day here on Earth. We need a way to tell our algorithms what images look like without imposing one type of image's features too much. One way we can try to get around this is by imposing the features of different kinds of images and seeing how the type of image we assume affects our reconstructions. If all images types produce a very similar looking image, then we can start to become more confident that the image assumptions we're making are not biasing this picture that much. This is a little bit like giving the same description to 3 different sketch artists from all around the world. If they all produce a very similar looking face, then we can start to become confident that they're not imposing their own cultural biases on the drawings. One way we can try to impose different imagey features is by using pieces of existing images. So we take a large collection of images and we break them down into their little image patches. We then can treat each image patch a little bit like pieces of a puzzle. And we use commonly seen puzzle pieces to piece together an image that also fits our telescope measurements. Different types of images have very distinctive sets of puzzle pieces. So what happens when we take the same data, but we use different sets of puzzle pieces to reconstruct the image? So let's first start with black hole image simulation puzzle pieces. Okay, this looks reasonable. This looks like what we expect a black hole to look like. But did we just get it because we fed it little pieces of black hole simulation images? Let's try another set of puzzle pieces from astronomical non-black hole objects. Okay, we get a similar looking image. And then how about pieces from everyday images, like the images you take with your own personal camera? Great, we see the same image. When we get the same image from all different sets of puzzle pieces, then we can start to become more confident that the image assumptions we're making aren't biasing the final image we get too much. Another thing we can do is take the same set of puzzle pieces, such as the ones derived from everyday images, and use it to reconstruct many different kinds of source images. So in our simulations, we pretend the black hole looks like astronomical non-black hole objects, as well as everyday images, like the elephant in the center of our galaxy. When the results of our algorithms on the bottom look very similar to the simulation's truth image on top, then we can start to become more confident in our algorithms. And I just really want to emphasize here that all of these pictures were created by piecing together little pieces of everyday photographs, like you take with your own personal camera. So an image of a black hole we've never seen before may eventually be created by piecing together pictures that we see all the time of people, buildings, trees, cats, and dogs. Imaging ideas like this will make it possible for us to take our very first pictures of a black hole and hopefully verify those famous theories for which scientists rely on a daily basis. But of course, getting imaging ideas like this working would never have been possible without the amazing team of researchers that I have the privilege to work with. It still amazes me that although I began this project with no background in astrophysics, what we have achieved through this unique collaboration could result in the very first images of a black hole. But big projects like the Event Horizon Telescope are successful due to all the interdisciplinary expertise different people bring to the table. We're a melting pot of astronomers, physicists, mathematicians, and engineers. And this is what will make it soon possible to achieve something once thought impossible. And so I'd like to encourage all of you to go out and help push the boundaries of science, even if it may at first seem as mysterious to you as a black hole. Thank you.
Wow, that's amazing. You know, again, if you think about the way that was done in Event Horizon, again, it's the way that we're reconstructing what a number of things might look like. When the Notre Dame Cathedral in Paris caught fire, artificial intelligence was used in the same way to reconstruct what that cathedral should look like, what it did look like before the fire. So it's used for a lot of different applications. One of the things I want you to really pick up from Katie's presentation there, again, we try to use data not to confirm, but to learn. And so what she was doing there was testing the algorithm against different buckets of picture pieces there to see if she rendered the same photograph based on the radio wave measurements, and she did. So that application of AI is incredible, and you see behind the scenes how it really works in a practical application. Well, one of the more new and one of the more interesting applications of machine learning is also in blockchain. As I talked about earlier, this is a distributed, decentralized, and public digital ledger that's used to record transactions across many computers. What that means is that those computers, and you can see over there to the right, the constellation of computers, they are gathering data, they are inferring from it, and they're sharing it and reteaching each other. So it is a network of learning technology. It's something very, very different. It's going to revolutionize the way we give voice to transactions, the way we give voice to inventory that had no voice before, and how we organize that, how we share it, and how we authenticate it. So let's take a little peek into the basics of blockchain.
While this was its original purpose, blockchain is capable of so much more. Despite the sound of the word, there's not just one blockchain. Blockchain is shorthand for a whole suite of distributed ledger technologies that can be programmed to record and track anything of value, from financial transactions to medical records or even land titles. You might be thinking, we already have processes in place to track data. What's so special about blockchain? Let's break down the reasons why blockchain technology stands to revolutionize the way we interact with each other. Reason number one, the way it tracks and stores data. Blockchain stores information in batches called blocks that are linked together in a chronological fashion to form a continuous line, metaphorically, a chain of blocks. If you make a change to the information recorded in a particular block, you don't rewrite it. Instead, the change is stored in a new block, showing that X changed to Y at a particular date and time. Sound familiar? That's because blockchain is based on the centuries-old method of the general financial ledger. It's a non-destructive way to track data changes over time. Here's one example. Let's say there was a dispute between Anne and her brother Steve over who owns a piece of land that's been in the family for years. Because blockchain technology uses the ledger method, there is an entry in the ledger showing that Adam first owned the property in 1900. When Adam sold the property to Dave in 1930, a new entry was made in the ledger, and so on. Every change of ownership of this property is represented by a new entry in the ledger, right up until Anne bought it from their father in 2007. Anne is the current owner, and we can see that history in the ledger. Now, here's where things get really interesting. Unlike the age-old ledger method, originally a book, then a database file stored on a single system, blockchain was designed to be decentralized and distributed across a large network of computers. This decentralizing of information reduces the ability for data tampering and brings us to the second factor that makes blockchain unique. It creates trust in the data. Before a block can be added to the chain, a few things have to happen. First, a cryptographic puzzle must be solved, thus creating the block. The computer that solves the puzzle shares the solution to all of the other computers on the network. This is called proof of work. The network will then verify this proof of work, and if correct, the block will be added to the chain. The combination of these complex math puzzles and verification by many computers ensures that we can trust each and every block on the chain. Because the network does the trust building for us, we now have the opportunity to interact directly with our data in real time. And that brings us to the third reason blockchain technology is such a game changer. No more intermediaries. Currently, when doing business with one another, we don't show the other person our financial or business records. Instead, we rely on trusted intermediaries, such as a bank or lawyer, to view our records and keep that information confidential. These intermediaries build trust between the parties and are able to verify, for example, that yes, Anne is the rightful owner of this land. This approach limits exposure and risk, but also adds another step to the exchange, which means more time and money spent. If Anne's land title information was stored in a blockchain, she could cut out the middleman, her lawyer, who would ordinarily confirm her information with Steve. As we now know, all blocks added to the chain have been verified to be true and can't be tampered with, so Anne can simply show Steve her land title information secured on the blockchain. Anne would save considerable time and money by cutting out the middleman. This type of trusted peer-to-peer interaction with our data can revolutionize the way we access, verify, and transact with one another. And because blockchain is a type of technology and not a single network, it can be implemented in many different ways. Some blockchains can be completely public and open to everyone to view and access. Others can be closed to a select group of authorized users, such as your company, a group of banks, or government agencies. And there are hybrid public-private blockchains too. In some, those with private access can see all the data, while the public can see only selections. In others, everyone can see all the data, but only some people have access to add new data. A government, for example, could use a hybrid system to record the boundaries of Anne's property and the fact that she owns it while keeping her personal information private. Or it could allow everyone to view property records, but reserve to itself the exclusive right to update them. It is the combination of all these factors, decentralizing of the data, building trust in the data, and allowing us to interact directly with one another and the data, that gives blockchain technology the potential to underpin many of the ways we interact with one another. But much like the rise of the internet, this technology will bring with it all kinds of complex policy questions around governance, international law, security, and economics. Here at the Center for International Governance Innovation, we seek to bring trusted research that will equip policymakers with the information they need to advance blockchain innovations, enabling economies to flourish in this new digital economy.
Okay, so you can see blockchain, many different capabilities there. I think the biggest thing that is new in this is the ability to authenticate. We can build levels of trust. Now, let me tell you how that might affect you as you're progressing through your educational journey. One of the things that you get is a degree for every time you achieve the requirements of an MBA or an undergraduate, or if you're a concentration major, you go in and create, you accomplish whatever it is that is required of that. And you're given a degree. That degree is recorded at the university. Well, the way that's going to change is that degree accomplishment is going to be recorded not only at the university level, it will be recorded on your mobile device. It will be a digital certificate, perhaps in LinkedIn or in some other technology that authenticates you as a bona fide MBA graduate of Kenan Flagler Business School, or as someone who has accomplished all the requirements of the technology concentration. You carry that with you. That can be authenticated on a local network. So if you go to apply for a job at Cisco, then you can be authenticated as the holder of that degree using digital certificates and using the blockchain technology. It's also going to be very prevalent in medical technology. You go to one doctor for perhaps pain in your knee. You go to another doctor for maybe a respiratory problem. The data that is collected at the two different doctors' offices is never seen by either doctor. Well, in blockchain, that data is revealed. So your medical records become part of a blockchain. So we move them to transactions, we move them to a decentralized type of environment, and we add artificial intelligence to authenticate and to transact across different infrastructures. In this very busy diagram, which I think is actually quite cool, you can see sort of the blockchain ecosystem explained. In all of the red, if you look at the red, just focus on the red lettering there, you can really see from identity management, authentication, all the way to supply chain compliance, traceability, smart contracting. This is where blockchain is going to impact industries. It's going to have a revolutionary impact, and it's going to change a lot of the way we purchase and transact different goods and services. I would say that in terms of its manifestation, blockchain is still in its early stages. Certainly a lot of people equate it to Bitcoin. That is one application of it in terms of what it might do. So it's something to be aware of. It's something that is evolving rapidly, and it is something not based so much in information sciences purely. It's in the computer sciences as well, in terms of artificial intelligence, being able to track and transact in a distributed manner using mobile devices, using digital certificates, and improving authentication in all sorts of transactions. So blockchain, let's go to the final one. This is one of my favorites. I love it. Can't get enough of it. It's great. This is rock and roll right here. Quantum computing. Quantum computing is something that started out as a theory, and now it is actually making its way out into first form technology. This is going to change everything. Now, at the beginning of our little conversation today, I started talking about problems that have gone unexplored that will now be able to be explored. The pathway to solving complex problems is quantum computing. And so what you're doing here, it is based in physics. So it's based in certainly a rock solid science. Although I did not do well in physics, I certainly understand its application here in the computer sciences. Quantum computing is going to revolutionize the speed and the representation and the calculation of data. If you think computing is good now, you haven't seen anything yet. What is ahead is amazing. So first of all, to understand quantum computing, let's go to the world we now know. And now you probably at some point in your career saw this or heard about it, bits, bytes, and a word. This is the way computing is done today. It's based on binary numbers, really more truthfully on and off states. Computer technology is based on electricity, and that is a light cutting on, you can see that, or a light cutting off, on and off. And so digital pulses are basically on and off states. Now a bit is the smallest size. This is the size that can store one digit or a binary number of 0 and 1, or an on and off state. A byte is 8 bits, which can store 8 zeros and ones. Now, hold on just a minute. An interesting thing about a byte is that you have 2 states that can be represented across 8 slots. So the different numbers of combinations of zeros and ones is 2 to the 8th. That's important because that really represents tunnels through a computer system. Word size or byte size really gets into this idea about how much memory can be represented. If my memory representation is only 8 bits, I've got 2 to the 8th possible combinations there. So that is the limit. That's the limiting factor of a computer. If I only have a word size in a computer that is 8 bits or 8 lanes of traffic, that really talks about the throughput. Another piece of the throughput is the amount of hertz. Again, we measured that in terms of radio waves earlier, but now we're talking about it in terms of just cycles going through, the speed at which those data goes through. So if you think about a computer and its word size, it is the amount of lanes and how fast something can travel through those lanes. And here you can see in the bottom a word size 32, 64, 128 sometimes. But what you're really looking at here, however many they are, is the number of lanes, which is word size, and the speed in which those digits travel, which gets into your hertz, megahertz, gigahertz. And that really gives you the computational power of the computer. So think about that just for a minute. How might we be able to represent more and to improve the computational power of a computer? Pause for a moment. It gets into the very first thing there, a bit. A bit can be 0 or 1. A byte is 8 bits. We can have 2 to the 8th representations of bits in a byte. What if, and keep in mind that's your number of combinations, so let's move forward here. If you take a look at 4 bits, 16 combinations, 2 to the 4. One way to drastically expand computational power is to change the definition of a bit to what's called a qubit, where it can represent more than just a 0 or a 1. That is the world of quantum computing. Rather than just on and off states, we can have in between states. It's like a coin toss. If I toss a coin, that coin is spinning in the air. When it lands, it can have 2 states, heads or tails. In quantum computing, it can also represent the in-between states as its flipping type of states. So that revolutionizes the world of computing quite drastically. So let's take a look at it. And this is called superposition. In classic states, you have true on, true off, so 0, 1. Take a look to the right. Quantum state starts to get 2 to the n paths. Now, one of the things that's interesting about exponential arithmetic, when you see something 2 to the power of something, is you start to really accelerate when that n starts to get higher. It starts to really become dramatically a lot more states that can be represented there. So these quantum states give us greater computational power. We can represent more in memory. We can communicate more across a bandwidth, across a wireless network, and we can compute more inside a computer technology itself. Let me show you an example. So this is basically when you're looking at a chemistry example and you're trying to simulate the cluster on the far left. So look at the F cluster there. Basically what you have, 1, 2, 3, 4, 5, 6, 7, about 8 states. If we're trying to do different combinations of that, you got 2 to the 8th there, different combinations of that particular cluster. When we start to combine it with the P cluster, we double the amount of combinations. In the M cluster, you triple and quadruple the amount of clusters. That starts to tax traditional computers. So if you imagine a computational situation where you're trying to look at different combinations and trying to produce a remedy for a particular virus or infectious disease out there, you start to reach the capacity of traditional computing pretty fast when you get into exponential types of arithmetic and exponential types of situations. So just know when the combinations become enormous, you start to bump up against traditional computing power. So what you want to be able to do here is to test a lot of different combinations and test it quickly. This is where quantum computing comes in to change how computers represent data, the word size of a computer, and basically it's no longer bits and bytes, it's qubits, which can be several states beyond a 0 and or 1. And the way I think about it is it's not making traditional computing. If you think of traditional computing as a horse, you're not making the horse run faster. This changes computing into a hawk. It can fly, it can manipulate, it can do so much more. So traditional computational power becomes something entirely new, something entirely revolutionary. So let's take a look at how Google
What does that mean? It's a
has
major
done
breakthrough
this.
in computer research. Quantum computers are much more powerful than the ones we use today and can solve problems that normal computers often find impossible. Jacob Ward's in San Francisco with more on Google's big announcement.
Allison, pretty much everything in our lives involves a sort of rudimentary kind of computing. And I'm talking about everything. I'm talking about your blender. I'm talking about your phone. I'm certainly talking about things like my image being carried across whatever device it's being watched on. I mean, all of this happens using bits, ones and zeros in sequence, which is how all modern computing records and transmits information. And so the amazing part of quantum computing is that it can do things that no current computer can do. Google, in its announcement about this, estimates that it took about 200 seconds for its quantum computer to do a calculation that would have taken a normal supercomputer, even the highest end thing we've got today, about 10,000 years to accomplish. So, would have taken 10,000 years. They say it took only 200 seconds. That, as you can imagine, is an incredible breakthrough. Now, why do we care about this? Well, before you just say, you know, hey, nerd, what does this have to do with my life? Here's the really amazing thing about it. Basically, not only would your, phone and the transmission of data and all of this stuff be transformed by this, but all sorts of national security questions are really dependent on this ability to only have ones and zeros right now. So basically, the passwords that you and I use and that we use for all encryption is based on the idea that it would just take far too long, like let's say 10,000 years for a regular computer to overwhelm your password, to figure it all out. Well, it's a national security issue because with quantum computing, in theory, you could very quickly guess and break down a password or any other encryption scheme. I mean, really just like that, right? In this case, this kind of collapsing of a 10,000 year project to 200 seconds, that's the kind of thing it could conceivably do with a password. All of this is very far off in the distance, but it's an amazing thing. So our whole lives could be revolutionized by this. We're not just talking about random, math experiments like the one they did today. We're talking about the development of new medicines, of new materials, of artificial intelligence, all of which depends right now on this very limited language of computing that we use. So the idea here is that if they really begin to go forward from this, and this is just a first step, but if they begin to really be able to deploy quantum computing in the way that they imagine, suddenly we're going to be able to have all kinds of incredible breakthroughs in the materials we make and the artificial intelligence we build and everything else as we go forward. Now, one last thought here, Allison, before I go, because I think this is an important thing for those of us who are watching sort of big tech and how huge these companies have become and how powerful they are. It's notable that even though this incredible breakthrough is a matter of national security, the Trump administration has said it's going to commit about $1.5 billion to quantum computing. Meanwhile, China is throwing billions, hundreds of billions of dollars at this kind of project. It's not happening at the university or government lab level. It's happening inside a corporation, in this case, inside Google. And the other big players in the United States are Microsoft, IBM, other companies like this. It's really a mark of our age that this kind of, Kitty Hawk sort of breakthrough is not taking place at the government level or care of academia. In this case, Google, in fact, bought the lab, absorbed a lab from UCSB, University of California, Santa Barbara, and all its researchers, and still maintains a Santa Barbara presence, which is where this computer is. That's a funny indication of the moment that we're in. But putting all of that aside, the breakthrough here, the fundamental quantum computing potential and the way it could transform our lives, it makes this a very exciting day, Alice.
Wow, that is a lot. It's amazing. I'm not so sure that I'm up with him on the lack of university involvement. We actually have quite a bit of this technology at UNC. Certainly schools like Virginia Tech, NC State also have computing labs in this. So one thing that we can say about quantum computing, it is rock and roll. All right, that's all for us today. I'm sorry this session went on a little longer. I got carried away. I got excited. I'm sorry, but there was so much to tell you, so much I wanted to share with you. I wanted to make sure that you got it all and that you understood this amazing frontier of artificial intelligence. The next time we dial in together, we will change the frequency of the radio station a little bit, and we will move on to nanotechnology, and then we will conclude the technology piece of this with robotics. Again, I hope you're excited. I hope you see the possibilities out here. Machine learning, artificial intelligence, an incredible frontier. Stay safe, keep things fun, and keep optimistic. There's an incredible world out there beyond our stay-at-home world today. It'll be summertime soon, and we'll be out and about once again. I'll see you next time. Take care. Until then.